Hi there, welcome to your emergency review for our recent assessment on linear and quadratic functions. In this video, we're going to look at paper 2. Okay, so from the math test, we had a question that said this: find all possible values of x such that this sequence is geometric. If this sequence were to be geometric, it would have to have a common ratio. And the way we find a common ratio is by dividing one term by the previous one. So the ratio must be 36 over 3x minus 7. Likewise, the ratio must be 24x plus 42 over 36. That one over this one. Alright, so there we have our common ratios. Those two must be the same. Therefore, we can set those two expressions equal to each other. Now we have a equation that can be turned into a quadratic. We can cross multiply 36 times 36 and then 3x minus 7 times 24x plus 42. So that's what I have here. 36 times 36, 1296, and on this side multiply that out to get this. Move the 1296 over that side to get a quadratic now, which is equal to 0. Means we can solve it. We can solve for x. That quadratic, you can use Pauli simulation number 2 on your calculator, or you can use the quadratic formula to get two solutions, 5 or negative 4.42. Both of those values substituted into x here will create a sequence that is geometric. You can check to confirm. Try one. Okay, so this one is very similar. We can begin by saying a ratio equals that over that, or the ratio equals that over that. Set the two equal to each other because r must equal r. Cross multiplying here. That becomes this side becomes that. Move everything to one side. You get this. That factors pretty easily into 10x times x minus 3, therefore x equals 0 or x equals 3. Both of those when x equals 3, because this question took it a little further. It said find the fifth term. So now that we know x equals 3, so I put x equals 3 in here, and I get a sequence of 20, 10, 5. And then the fifth term must be 1.25. We can notice it is a common ratio of a half, so it's multiplied by a half every time. Why did I not use 0? If you put 0 in here, you would get 2, negative 2, 2. The sequence would be 2, negative 2, 2, and that's a multiplier of negative 1. So that, well, you know what? That might work. You might want to try it for that one as well. Okay, let's look at another one from the math test. The second one on the test looked like this. Had Steph Curry taking a shot which follows a parabolic arc, means a parabola. The x-coordinates represent the horizontal distance from Curry, and the y-coordinates represent the height of the ball. So we can just see distance in feet both ways. During its flight, the ball passes through the location 513 and reaches a maximum point in its arc at this point. So maximum point right away tells you this is going to be the vertex. So we know the vertex and we know another point. If we know the vertex and any other point, we can make a model for a quadratic. If we don't know the vertex, we need 3 points. But if we know the vertex, 2 points is enough. So we're going to create a model for Curry's shot without using the quadratic regression on the calculator. So we'll begin in vertex form because we were given the vertex. Replace the h and k with those two values of your vertex here, negative 12.4 and 15.7. Then I need to find out what a is. So to do that, I take the other point I know and put it in there. So that replaces right here, 13 for the y and 5 for the x. That 5 minus that is this, square that, move the 15 over here to get negative 2.7, then divide by that, and you get your a value of negative 0.05. So now we know the model for his shot is this. Okay, next, B. Find the height at which the ball left Curry's hand. Okay, that means we're looking for the y-intercept because that would be the starting point in terms of distance from him, because the x values represent how far the ball is from him, and the ball is in his hand when it has no distance from him still. So we're looking for the y-intercept. Here's a graph just to help us visualize that. This is the point we want here because he's going to shoot from here, it's going to reach this maximum here, and then hopefully go in the basket here. So we're going to find the y-intercept by setting the x equal to 0. That's how we always find the y-intercept. We're saying the distance from him, x, is 0. So solve this. 0 goes in here. And you solve it, solve, you get 8.01. That is the height of the ball when it leaves his hands. Okay, C. It says Curry makes the shot. If a basketball hoop is 10 feet high and the three-point line is 22 feet from the hoop, so this distance 22, basketball hoop 10, we're going to try to see basically if the point 2210 exists on this parabola. So what I'm going to do is look for that. Set my equation equal to 10, because that's saying when is the ball that he shoots at a height of 10, So I put 10 in there, and now I'm going to solve this. I can graph on my calculator, graph this parabola, graph y equals 10, and look for those intersection points. When I do that, I find out that one of the points here is 2310. So that tells us that he shot the ball, and it says he made it, so he made it into the basket right here, 2310, and that is 23 feet away from him, which means he made the three-point shot because the three-point line is 22 feet. Okay, part D. If the ball were to continue on the same path until it reached the floor, so here it went through the basket, continuing the same path, hitting the floor here eventually, then how far would it be from Curry? Well, that point is clearly one of the x-intercepts that we're looking for there. So if we can find the x-intercepts, we can answer that question. So first of all, yes, 2310 tells us the three-point shot was made, and now we're going to find the x-intercepts. So solving that, and x-intercepts, you set the y equal to 0. Remember, for the y-intercept, we set the x equal to 0. For the x-intercepts, we make y 0, because y is 0 here when this is intercepting the x-axis. Set that equal to there. We can use the Poly Simulation app, and we can find this answer here. So we know the ball, if it went behind him, it would be at negative 5.32, but then the x-intercept over here past the basket is at 30.12. So the ball lands about 30 feet from Curry. Good problem, a basic kind of application of quadratic models, so make sure you take a look at those details again. You're ready to try one. Try this one out. Now we have James Harden, another great player, not as good as Curry, of course. Okay, let's check your work. First of all, creating a model for Harden's shot. Again, vertex form. We put in the vertex we are given. We put in the point we are given, 14, 15 here, and we solve for A. A this time is negative 0.041. Now that gives us our model for Harden, the full model. We have to show that the ball passes over a defender's hand who is 2 feet from Harden and has arms raised up to 9 feet like this. Alright, so that means we put an x value of 2 because that means 2 feet from Harden, and we figure out what the y value. In other words, when you put 2 in here, when the ball is 2 feet from him, how high is it? Because y represents the height. So I put 2 in there for x, and I found out the ball is at 10.8 feet, which is higher than the defender's hand, which was 9 feet. So he shot it over the defender's hand. Great. So the shot is going to go towards the basket now. It was not blocked. Let's see. If Harden took the shot from 24 feet from the basket, and again the hoop is at 10 feet, did he make the shot? So let's see if he made the shot. It tells us he is 24 feet from the basket. So I'm going to substitute x in with 24 again. I'm going to put that in there and say, hey, when the ball is 24 feet from him, how high is it? Because we're going to solve for y. How high is it? This, when we solve it, we find out the ball is at a height of 8.09. Well, that tells us he didn't make it, because at 24 feet from him, it had to be at 10 feet to be going right through the basket, but it was below the basket. So we can say that he took what's called an air ball. He didn't even hit the rim or the backboard. It just went under the rim. Terrible shot, but that's Harden. That's what we expect. Okay, from the test, we had a question like this. It said a town council was building a sports field, and it had only 380 meters, money for 380 meters of grandstands, so seating for all the crowds. And it could build the grandstands anywhere, including the middle, it said. And it said, let the middle count as one single row of grandstands. So that means all these blue lines here have to add up to 380 meters. So if I call that x, that's x, that's x. Call that y, that's y. That means 3 of those lengths, 3x plus 2y, must be 380 meters. Okay, we're also looking to maximize the area of the sports fields, or both of them together. So area is x times y, x times y. That has 2 variables, so we're going to have to use this equation to substitute here and simplify it. So I took this one, I solved for y. I did 380 minus 3x, then I divided by 2. And now I can take the area formula and replace y with all of this. That's the benefit of having two different equations to begin. So now this, if I simplify it, if I divide by 2, is 190 minus 1.5x. So that y was replaced by that right here. Now I have an area model that has only one variable in it, which allows us to solve it. Oh, there's that part, sorry, right there. Okay, now we have this area model when you multiply this, and that area model we can find the maximum point, because this will be a parabola and we're looking for maximizing the area. So I'm going to find the max point, and the max point is the vertex. So I'm going to put x equals negative b over 2a to find the vertex. Negative 190 divided by 2 times negative 1.5 is this, 63.3. That tells me to have a maximum area here, this x must be 63.3 because I solved for x. And if that's 63.3, we can find out y is 95 because I can put that 63.3 in here to calculate y. And I found out it's 95. So this is 95, this is 63. But the question was saying, what are the dimensions of each of the playing fields? So this one and this one. Well, each of the playing fields then will be 63.3 by 47.5 because 95 was the entire length, and now this is half of it, 47.5. So we have one of these has these dimensions. Okay, great. Try this one. Okay, let's see how you did. We have, we're going to create 3 practice rooms, so it's going to be like that. And we have soundproof walling, only 14 meters of soundproof walling. And it says we don't need the outside corners to be with the soundproof walling because it's already part of the music room. It already has soundproof walls. We just need to put the walls where the red is. So if we call that y there, and then these ones x again, we can say that 3 of these that we built, 3 partitions, 3x plus y, only one y, not 2y, because we only need to build here. 3x plus y equals 14. So all the red is our 14 meters. That can be solved for y. And then we can talk about the area. The area is x times y, or in other words, x times this, because y is this. So there's our area. That simplifies to this. And then we want to find the maximum. So we use negative b over 2a. And we find 2.33 is our x value. Taking that x value, putting it back in here, we get a y value of 7. So we find out that this must be 7, this must be 2.3. But 7 needs to be divided into 3 parts, which is actually 2.3 as well. So we found out that actually the 3 practice rooms are all going to be square-shaped, and they have these dimensions. Great, hopefully that one went okay for you. And we will pause there. For now, there will be a third video looking at the long response problem.